Excellent. Hi, everyone. Welcome back to our last in what has been a really long series of learning machine learning with Jason and myself. Hi, Jason. How are you doing, buddy?
Hey there, Glenn. Good to be back for our ultimate episode. You called the last one penultimate, so I'm sticking with that verbiage.
it will be the ultimate, the final countdown of today's session. So we're going to learn a couple of cool acronyms, ROC and AUC. Which will describe a little bit. I nearly brought my guitar in when I saw the ROC.
You're ready to rock then? Is that what we're...
I am. And I am. So in case someone's just watching this episode only and haven't been watching the series, Jason, do you want to introduce yourself to everyone?
Yeah, hi, I'm Jason DeBoever, Senior Product Manager here at Microsoft, working on AI and ML content, hence my presence here on this stream. And you, Glenn?
Well, I'm a senior content developer working on the Learn Live team.
Fantastic.
That's my summary.
And speaking of this content, this is where we're pulling it from, is this Learn module right here. And people can check out the Learn module for themselves after the session, of course, because we want them to hang out and listen to us for right now, right?
We do. So you can head over to https://aks.ms/learnml-optimize performance. And that'll take you to this specific Learn module that we'll be covering today. If you want to look at the entire path, just remove the -optimize performance, just do the /learnml, and that'll take you to the learning path that we're looking at.
Absolutely. We'll see the whole learning path there. In fact, we'll see all of the source material for all 9 episodes that we've had of this series. But in addition, there's a whole bunch more content that's in those learning paths as well. So when you go visit that learning path, you'll actually see a few different related learning paths linked and a whole lot of content, which will serve us well. I'll talk again about that at the end, because that'll be part of that where to go next. After these 9 episodes, we're going to leave you hungry for more, and that'll be how to sate that need. One of the ways to sate that need.
Cool. So stick around for that for sure. And we are live and interactive. So I think we're streaming out to Twitch and YouTube today. So feel free to add some comments. We'll see the comments sent to us as well, and we'll answer any questions that come through. But there's a few learning objectives.
I keep today as well.
That's all right. Do you want to take us through the learning objectives, Jason?
Yeah. So we're going to learn about those cool acronyms you talked about earlier. So we're gonna learn about ROC curves and what those are and how those can help us assess our models and choose our models and refine our models. And we'll also look at something that we do with the ROC curve called the area under the curve, which is just a way to measure the ROC curve itself. So ROC is an interesting acronym because we don't usually define it, because it stands for something irrelevant. I will define it for you in a little while. But first, let's talk about, again, the live and interactive nature of things. So you already touched on this, but yes, we definitely want people to jump in, say hi. We'll get those questions passed to us.
Yeah. You know what? I'd also be curious to know who's been sticking around for the entire series.
Yeah. If you've seen us all the way from episode 1 to episode 9, we'd love to hear from you.
Cool. Speaking of people who've been around for our series, speaking of the people who've been around for our series, our lovely moderators have been with us for quite a time as well.
Well, actually, I was going to give Daniel a special call out here, because he's the only moderator that's been with us from episode 1 all the way through episode 9. So he's moderated every one of our episodes. So Daniel, thank you very much. We're really glad to have had you. Really glad to have had the assistance. And thank you to our other moderators as well, not just the ones here on the screen for today, but for all of our episodes. Thank you all so much. All right, so let's start talking about ROC.
Let's do it.
ROC is receiver operator characteristics. It's a tough one to say, and you'll almost never say it because the derivation of that term is historic. I think it's from World War II, if I remember correctly, and has to do with like radio signaling. That's not how we use it today, so wouldn't worry about it. It's generally simply referred to in the trade as ROC. So the ROC curves. We'll talk about what those do and how we can use those to assess our models. and we'll talk about them in the context of a scenario, as we always do. So, Glenn, tell us about our mountain today.
Well, we're going back to the mountains for our scenario as well. And we've been visiting this scenario for a number of our episodes. So we have some drones that take cameras of the surroundings of this mountain that we're looking at and evaluating. And we essentially want to determine if there's a hiker on the mountain or not. And if in the event that there's an avalanche, we want to know if there is a hiker there, because that way we can send out a rescue team and go and get them. And we also want to minimize the errors for the context as well. So if it's detecting a hiker out there when there's really not, we don't want to send our rescue crew into dangerous situations when they don't need to. So there's a little bit of importance to this particular model today.
Yeah, there's definitely a trade-off. On one hand, we want to get our hikers rescued whenever possible. But on the other hand, if we simply scrambled the jets or the helicopters or whatever it is for every single remote possibility of a hiker, then we one, be just wasting resources, and two, potentially not have our rescuers available when something actually did happen. So while we want to err towards caution, we can't just always scramble the rescuers. So we need to figure out the right trade-off. And that's really what this episode is going to be about, is talking about how to manage our model to get those trade-offs right for us. All right, the receiver operator characteristic curve, ROC. Now we're ready to rock.
Excellent.
So let's think again about our classification models and how they actually work, especially what we talked about when we talked about logistic classification. This doesn't only apply to logistic classification, but it certainly is easiest to think about in terms of the way we described that model. And the output of those models, when we were trying to determine what class something belonged to, the output of those models was actually a number between 0 and 1, kind of a probability. And that probability is something that we can use to move our model's performance further once we're relatively happy, or at least once we're ready to judge its performance in terms of other models and in terms of the broader world. So we might not know we're done, but at least we want to kind of zoom out and take a broader look and see what we can do. And the ROC curve is one of the ways we're going to do that. Using the ROC curve is one of the ways we're gonna zoom out and look at it in different contexts. So we have those probabilities. And what I mean by that is when we're trying to guess, say, true or false, we're trying to get a model to guess something is true, like a hiker. It is a hiker or it isn't a hiker, right? So we're trying to get it to make that prediction. But the model itself, even though we talk about classification and we talk about it predicting if it's a hiker, the truth is the actual model itself is outputting a continuous value. We have it outputting a continuous value from 0 to 1. And then it's more our process, really our software that's holding the model, that's going to take that number from 0 to 1 and say, okay, well, obviously if it's 0.999, then we're calling that a 1. And if the model output 0.00001, then obviously we're calling that a 0. And by default, and especially early on in the discussion of these models, we assume that the cutoff is 0.5. We say, all right, well, if anything at 0.5000001, all right, that's going to go up because 0.5 is our bar. Everything above goes 1 and everything below goes 0. But we don't actually have to use numerical rounding rules. As it turns out, we can use any cutoff we want. We can use absolutely any arbitrary threshold that we want and say, all right, if it's 0.8 and above, then it's 1. But if it's 0.8 or below 0.8, 0.799999, then we're going to go call that 0. And it may seem extremely counterintuitive, but remember that the model didn't really know anything about what was going on anyway. We're just bending lines. And so once we're bending those lines, we can then arbitrarily start to look at what works better for the trade-off we want. And
so
fact,
we're really trying to optimize that value, though, aren't we? We're seeing if we can change that value of where the cutoff is, can we improve our model's performance?
Yeah,
That's
and what does that mean to improve performance? It goes back to that question about wanting to rescue every possible hiker, but not scrambling the helicopters for just every leaf blowing in the wind on the mountain. So we want to be able to make the appropriate trade-off. And the appropriate trade-off is not necessarily always immediately obvious, but also, also optimizing it in terms of even an easy metric. It might not be the 0.5 cutoff. It might actually turn out that some other threshold just works better. And that's what we start to evaluate with the ROC curve. Now, in order to understand what we're going to do with the ROC curve, go back in time to our previous episode and talk about our confusion matrix and how we looked for our true negative, our true positive, our false negative, and our false positive. And actually today we're really going to focus on those true positives and false positives. So in other words, where our model predicted a true. So our model predicted yes hiker. And remember, sorry, when I say predicted true, I'm saying positive, right? So it predicted positive. When we say positive, that means predicted true, which is a little confusing because then we use true and false as a modifier, which definitely ends up causing some jargon. But what this means is correctly predicted true, correctly predicted positive, and this means incorrectly predicted. So let me get my laser pointer here again. This means incorrectly predicted positive, and this means correctly predicted positive. All right, so that's what we mean when we say true positive and false positive. All right, so let's turn that laser pointer back off and look at how we're going to chart those true positives and false positives to start beginning to build a ROC curve. So again, notice that I've got true positive here on my y-axis and false positive here on my x-axis. So based on that confusion matrix that we saw first, I've plotted a point. So I have a single point for that confusion matrix. And that may not look much like a curve at this point. In fact, it doesn't look anything like a curve at this point. And previously, when we looked at our confusion matrix, we only got one true positive and one false positive because we only got one confusion matrix. So how are we going to get multiple points? The answer is we're going to use different thresholds. So before we built that confusion matrix and before we calculated our true positive and our false positive, we also selected a cutoff. So our model output some numbers between 0 and 1. We took our cutoff and mostly we were using 0.5 as the cutoff. We took our cutoff, and then we now knew whether I predicted it to be a hiker or predicted it to not be a hiker. So that prediction needed to know the cutoff before we could start categorizing things into true positive and false positive. So that's how we derive that single point. But we can pick a different cutoff. So now we pick a different cutoff and we end up with a different trade-off of true positive to false positive. And so we chart that as well. And we just keep doing that for lots and lots and lots and lots. Theoretically, just all possible values of threshold, but of course, you could have infinite, so we're not really doing all of them, but enough of them to kind of derive that curve, right?
But it's not really a curve in the linear sense. It's actually just a scatter plot. It might be that certain values don't exist within a range because of the way it's calculated.
Yeah, and it's interesting because, I mean, theoretically, it could, if we were able to chart an infinite set of values, we would have a line because it would be a continuum if we were able to chart an infinite course of these different points. But when we pick our cutoffs at kind of an interval, so let's say that our interval is a tenth, right? So like we know everything is 0 to 1. So let's say that our interval is we're taking our 0.1, 0.2, 0.3. We're trying each one of those as a cutoff or as a threshold, or even hundredths. So we have 100 different points. So we have 0.001, 0.002, or 0.01, 0.02, right? Regardless, if we start to pick a set interval, one thing that we will notice is that these are not equally spaced, or they're not predictably spaced, because some choices of threshold are barely going to move the needle at all. So you're not going to get more true positives or more false positives. You're just not going to move the needle much at all. So you're going to have very, very close clusters. Other times you're going to move it just one little notch, and all of a sudden you're going to get a big jump because there are samples there happen to be a lot of samples near that threshold. And so when you do that, you're going to see a big movement. And this chart right here only shows us the behavior of true positive relative to false positive. It doesn't actually directly show us what the cutoff that we chose for that dot is. Now, of course, if you're clever in how you do your visualizations, you could build it such that hovering over one would tell you what the the cutoff chosen was. But the ROC curve itself doesn't. It's only showing the relationship of true positive to false positive. Now, the next interesting thing, and let's go ahead and fill out the line. So like Glenn said, there's as we do it in practice, we essentially get ourselves a scatter plot. But we can think of it as a line by just drawing the line through it. And in reality, if we were able to have infinite points in between to measure, we would see a line. But notice that the line will always go kind of up and to the right. And what we're looking for is the bubble in between. But the reason it's always going to go up and to the right to some extent is because we're essentially always moving towards guessing everything positive. And what I mean by that is if we go all the way over to this point right here, this is 1 and 1. That means that I'm essentially guessing everything's positive. So I managed to successfully guess all of the things that should be true. I managed to say, yep, they're true. But I also took all of the things that shouldn't be true, and every last one of them said, yep, it's true. So in other words, I guessed true for everything. So my false positive rate and my true positive rate are all 100%. Every possible false positive, I got it. Every possible true positive, I got it. So that's what happens here. Contrarily, if I guess everything negative, we're down here. So I didn't get any of the things that should have been positive accurate, or should have been true accurate. And I did not get any of the things that should have been false accurate. So that's down here. And that's basically if my threshold for picking was like 0.9999999. I say everything below 0.9999999 is going to be false. So I did that, and now I guessed everything false, and we get pretty bad performance. And this is the opposite, right? So 0.000001 is my threshold. So now, and then everything else is what happens when we do things in between, which of course tends to be the more interesting question. If we apply this to our hiker model specifically, you can see that we kind of have a way of thinking about, of characterizing what false positive means. So this is, we identified non-hikers as hikers. So that's what a false positive is in this case. We're looking for hikers, is hiker, and this is not a hiker. So that's a false positive when we call it a hiker. And then of course, this is where we call a hiker a hiker. All right, that is our gentle introduction into ROC curves. And now we're ready to move on to a demo that is code.
Excellent. So I'll just move over to my screen as well.
Fabulous.
And we're going to look at basically the ROC curves. There's a few examples we'll look at. We'll look at basically what a perfect model ROC curve looks like. One that's essentially like flipping a coin. One that's absolutely terrible, and something that's a little bit more realistic, just as we go through it. So we've got our screen here. Hopefully you've activated your sandbox. You've logged in, used the sandbox. I think I've got about an hour left. And we're going to go through a similar process to what we do in most exercises, which is to essentially bring in some data. In our case here, we've got a hiker or tree CSV file that has all of the data we're looking at. We're mainly interested in to see if there's a hiker there. It's almost that classic hiker or not hiker, hot dog or not hot dog. And we've got our CSV file. We're reading that into the pandas library. We're also then creating our training set and also our test set. So it's a bit of a size difference here. We're using 50% for our test size, which is interesting. And we'll also draw some charts as well. The charts are going to be interesting to look at. This will take about 20 seconds to run. So I'll just look at this. I'll run it now, and then we'll look at it. So we'll look at the height and how that relates to if it's or not. Likewise with the motion or the texture. So it's still executing.
And we're still not super clear on what texture is, but data sets be data sets. And we don't be domain experts in this case.
I worry that they're like putting some sensors on to see how spongy a tree or a hiker is.
It's so
I'm not exactly sure why. Yeah. So it looks like it's still executing here. I can't see my charts just yet. But the chart should give us a sense of where the correlations lie between the particular features and what we're looking for, which is whether they're a hiker or not.
And the most interesting thing, I know that once we get it to show up, you know what? It's not scrolling your inner scroll bar right now. You've got a nested scroll bar there. Is that?
I know. I was looking for this.
I see. Yeah, it's still executing there. That's weird. This one never takes that long to execute. Of course, now it does. That's never happened. But yeah, the most interesting thing I think that we'll see, of course, you know this, Glenn. But for the folks at home who are waiting to see it, we'll see that some of the features we have in there are going to be very, very easily and directly correlated to creating a perfect and easy model. In other words, a model that just never gets it wrong. And then some other features, if we choose to train using only those other features, we're going to have essentially randomness. So something that's not very useful for making a prediction. Hey, there it is. This is
we have the charts here. And if we look through the charts, the first one we're looking at is a histogram of basically what their height is and whether or not they're a hiker. So looking at the data, it's actually pretty clear when we look at the height. I'll just move that up. That we have all the hikers essentially looks like they're less than about 4 meters tall, and everything else, which is not a hiker, is greater than 4 meters. So that's actually pretty interesting.
There's a couple things to take note of. One is that it looks like we have at least one hiker who's got to still be like 9 foot tall, which is pretty crazy.
Yeah.
So that's like pushing 3 meters. So
yeah,
that's interesting.
Personally, I think that's Bigfoot right there, not a hiker.
But other than that, the interesting thing is that clearly we could easily and will easily train a model that can use height to but just perfectly guess hiker or not hiker, because there's just absolutely a perfect line that can be drawn right down the middle there. And so that's going to be useful for proving out certain things about our ROC curves, but it's interesting to see that it's clearly true. Excellent.
Yeah, agreed. Now, if we scroll down a little bit further, we see the motion though. And the motion is a little bit different. Let's see if I can move this window out of the way.
You just hit that hide button, actually. Oh, there we go.
Oh, yeah. That's a good option. All right. So in our motion, we can see that when there's a little bit of motion, it's not being detected as a hiker, or sometimes it is. There's a little bit of overlap here. And it might be that the hiker is actually just tired and they're resting for a little bit, so that they're moving just as much as the tree would. And the trees might
just to clarify, so you said not predicted as a hiker, but or not identified. But remember, this is our ground truth. just to be clear. So it's not whether this was recognized as a hiker by our model yet. Right now, we're just looking at our raw data. So this is the ground truth. This is what we're going to train our model on. So let's assume that whatever we used to gather this was just absolute correct. We hope.
Yeah. So it looks like if you're moving pretty fast, or faster than about, I think the unit is 1 meter per second, then it's likely that you're a hiker. But if it's below that amount, there's some probability being mixed in. That's what our model will probably end up with. So this is going to be not as ideal as the height, but we can still. And then if we look at that texture, well, there's no easy correlation that you can get. It's probably a bit of guesswork there. So let's actually put that into practice. And we on with texture with all of those elements. We may do.
We might have a delay going
I am calling from the other side of the planet. It's amazing that we're doing so well. All right, so we have our stats model. We're essentially doing a prediction based on this. So we're looking at the model. It's just executing. Here we go. And this is essentially using the height, I believe. So if we look at the height and the hiker, we can see that the predictive model, which I think is, just doing a scatter chart, that we've got our hikers all coming in at the right value, and anything that's above that 4 meter mark is coming in as not a hiker, which is what we really want in this particular case.
Yeah, so it means that
our prediction is going through the points.
We definitely have a delay. It means that as we guessed, we were easily able to create a model, in this case, a logistic model that can knock it out of the park and give a perfect estimation. And of course, that we get to now see what that looks like when we plot our true positive rate and our false positive rate.
Cool. So our next code snippet is really just calculating the true positive rates. It's also looking at the false positive rates here as well, but we're only interested in the positive rates here for our ROC curves. So it's getting those particular values, calculating the true positive rate and the false positive rate.
Yeah, and really quickly, when we say true positive rate, let's remember that's a percentage. That's what we call it, the rate, rather than just true positive. And you can see right there that what we're doing is saying the true positive rate is the true positives over all of the things that were guessed to be positive, which would be the true positives and the false negatives. I'm sorry. So it's actually the true positive rate is all of the things that should be true. My mistake. Not all the things that were guessed to be true, but rather all of the things that should have been guessed to be true is what that rate is. So it's a percentage of how many things we accurately guessed true or got right.
Yeah, and likewise with the false positive rate as well. So it's all the false positives over all the things that should be positive, should be negative. In this case. So we've got that calculation. It's returning those two values, which we'll use for the ROC curve. And then we've got the assess model, which is basically looking at those. It's really defining a method that we'll use when we create our ROC curve in just a second. So it'll test against the particular feature, look at the prediction of if it's a hiker, and then calculate that true positive rate and false positive rate for a particular threshold. And then we'll essentially cycle through a range of thresholds when we create our ROC curve and get that false positive rate and true positive rate. And we'll add that into an array, and then we'll essentially collect those values for each of the values that we're iterating through, 0 through to essentially 100.
And to once again point out, we're using the same model every time. So when we're looping, we're using the same model. The model will take that data, and it does take our input data and output a guess for whether something's a hiker or not, right? So it outputs that number though between 0 and 1, and it's that number, that 0 and 1, or 0 to 1, that is getting applied a threshold to basically round it up or round it down to 0 or 1. to true or false. And so it's that we're changing that threshold, but the model's giving us the same number for each record every time we do this. It's not, we're not changing the model. We're getting that same probability out. It's just how we react to that. And I say probability, you should take that with a grain of salt, because obviously it's not proper probability if we're able to just change the ratio, change the threshold to change what we're predicting. But we use the term loosely, but we use it.
Yeah, fair enough. So you can see our thresholds here. We're iterating through them, assessing the model for that particular threshold, and then adding it to the true positive rates and false positive rates. And then we're graphing the chart based on that
based on a full set of those.
Yeah, and if we're looking at the height, for example, the height is an amazingly good predictor of those values. So when we see the ROC curve here, we're seeing something a little bit unique, where it's kind of interesting. You were explaining this before, Jason, but we've essentially got a line that's going up and over, and but there's actually less points in reality.
Right. The thing is, one thing that we do when we make this graph is we kind of force the first point, or the start of the line, the trend line, to go through the origin 0, 0, and we kind of force the 1, 1 point at the top right. The reality is, because this is a perfect model, we are actually if you go back to that scatter plot that we first used, that we first identified things on.
You mean on the slide deck?
Oh, we don't have it here. It was in the slide deck. Yeah, I didn't mean for you to go back to it. I just meant for our viewers to think back in their brains to that scatter plot. So if they think back in their brains to that scatter plot, then you can imagine that every one of our thresholds is giving us a point, a dot that needs to be plotted on here. And I said that it always goes up and to the right. This is the exception, one of the two exceptions, because in this case, we have a perfect model. I suppose that you could probably get small enough. You could probably get a threshold small enough that you actually would, like 0.0, infinite zeros, 1, that you could probably actually get a zeros, an all wrongs or an all rights. But in truth, for all practical purposes, every one of our threshold values is going to be at the TPR, or true positive rate, being 1. In other words, we successfully guessed all of the trues as true. So all of our dots are going to be there. And we also successfully guessed all of the falses as falses. So we never had a false positive. We never said our model never said it's true when it shouldn't have been true. And so we are able to basically have this perfect model that got zeros and ones right off the bat. And it was it was irrespective of where our chart was, because our logistic chart didn't have to asymptote towards that. We didn't get a lot of guesses, or any guesses that were, say, 0.75, where the threshold mattered a lot. So yeah, we actually should end up with all of our guesses as perfect in that spot. In theory, like I said, if we actually use, say, 0 and 1 as the cutoffs to where there were no data, then it might be able to change things. But for practical purposes, our model was so perfect that all of the threshold choices were probably up in that top left of perfection.
Cool. So let's move from a model of perfection to a model of awfulness then.
Yes.
So we're going to look at a very, very bad model. So in this particular case, we've got a prediction where it's really just flipping essentially is hiker. So it's predicting if you're less than 4 meters, you're probably not a hiker. And if you're more than 4 meters, you're probably a hiker, which is the opposite of what our real data represents and what the curve represents. So in this case,
our model got nothing right.
No. It's a F for failure on this particular one. So it's not a great system, but if we look at the ROC curve for it as well, it's almost the flips of the of the one we had for the perfect model. So where realistically, we've just got that situation down here where the false positive rate is 1 because they're all being detected wrongly, and the true positive rate is 0. So you can't really get anything worse than this.
Exactly. You quite literally can't get anything worse than this. So yes, everything, all of even our very first data point jumps to false positive rate, which is everything is guessed wrongly. And our true positive rate is nothing is guessed correctly. So we're just in the bottom right all along.
Cool.
Boo model.
All right. Well, let's go to another model as well. This time we're going to go back to the texture. So you and I both don't know really what the texture represents. When you look at the histogram, the data is almost even. Like you're really just guessing it.
Yeah, which means it turns out that our model doesn't have a clue what the texture is either. It's just it's just 50-50.
Yeah. So we've actually got a question coming in. If I get a perfect model based on my real data, just what you showed, do I have simply a best model, or is it suspicious? I love that question.
Yeah, that is a good question. I mean, if you can get a perfect model, it's also probably really easily justified or explained. It's probably quite easy to do the data analysis. See, oh yeah, of course we got a perfect model. We didn't even need to use machine learning to do this in most cases. So I would say that you know, if you got the perfect model, you're able to do a little bit of analysis and justify it, then you probably just have simple data, which is great. Otherwise, it might be a little suspicious if you can't see where that perfect model came from, and if you can't recreate it with new data, then I would definitely be suspicious.
Yeah, and making sure you've got verification data as well to run against it. It's pretty important.
Yeah, but I mean, if your data set included speed and you had some things that were going 50 miles an hour and some things that were going 1 mile an hour, you'd probably have a pretty good, or less than a mile an hour, you probably have a pretty good data set to get a perfect model on whether something is a car or a human. So just like our height was perfect, is a perfect model possible? It is. It may not be the most useful way to analyze your data if it's that easy, but it's possible.
Cool. All right. Well, let's get back to our model here where we're looking at the chance. So we're using the texture here to train the data to determine if it's a hiker. And when we run this one here, we'll actually see something slightly different in that our prediction curve actually doesn't go through any of the points. And if we look at our dots, there's not really a correlation like we had in our perfect model, where we'd see that the curve would actually go through not almost, but all of the dots within that curve.
Yeah.
But this is not. Oh, go ahead,
I was just going to agree, but we have a little delay, so it makes my agreement awkward.
All right, well, we'll get the ROC curve here based on the texture. And you can see that it's actually just a diagonal line. It's not quite a diagonal line, but it's pretty close to it. And in fact, in the chat, we've got another question. So the possible values for all ROC is from 0.5 to 1. Being close to 1 is too good to be true, is one of the comments. But we're talking about the area under the curve, and in our perfect model, there's a lot of data here. I'm probably jumping ahead of myself.
Yeah, the question referenced AUC, which we haven't talked about yet. So I'm not quite sure I understand what they're asking. So why don't we wait until we actually talk through the AUC, the area under the curve, a little bit in our next section, and then maybe we can revisit that question and see if maybe we luckily answered it, and if not, we can try to revisit it with what we have discussed and maybe have a little bit more clarity on what they're looking for from us.
Cool, good call. All right, so here's our chance model essentially. So it's a diagonal line.
So let's kind of address this and talk through this a little bit, because I think that the chance one is almost more interesting, because no matter how we did this, we would have a lot of, we did our scatter plot, we'd have a lot of data points, and that makes it really interesting to talk through. So we have our scatter plot and we are getting these data points, but we have a model that doesn't know anything, right? It basically doesn't know anything. It's essentially as good as guessing. So why does it move at all? Well, the answer is because we essentially have a model that's going from guessing no positives at all. So if my model guesses nothing to be true, then of course it has no false positives and it has no true positives. It's down at the bottom. Now, if in my total data set I have 100 accurately positive, right, 100 that should be positive, I have 100 of them. 50 of them, and I guess 100 of them, right? 50 of them are true positive because due to randomness, I got 50 of them correct. And due to randomness, I got 50 of them incorrect. So in that case, I would be, right where Glenn's putting the crosshair. So I would be at 50-50. If I guessed 40 and 40, I guessed 80 total. 40 of them would be correct and 40 of them would be incorrect. So it'd be a little farther down. In other words, because our model is no better than random, we're always going to be at equivalent. 20-20, 40-40, 80-80. And it's just a function of how many positives did we guess. How many positives did we guess is just a function of where our threshold is. So remember, if our threshold was down at 0.00001, then we'd guess basically everything positive, and we'd have a 50-50 way up at the top right. And if we guessed everything negative, then we'd have our 50-50 because we had our threshold of 0.9999, and we have everything at the zero. And then, like, again, everything in between. So it's just a function of our threshold, how many positives we guess, but they're always going to be distributed half towards correct and half towards incorrect because we have a random model.
All right, well, let's go back to a realistic model then. So in this case here, we're going to train it on the motion. So the motion, we had a little bit of overlap within the chart that we saw. So it wasn't quite as good as the height, but we could at least look at it, and it's probably a little bit more realistic from what you might see in your own models. So we'll go ahead and train that. A logistical regression, the motion. And we have a look at the chart. We can see that there's our normal curve. It's picking up a lot of the hikers, not necessarily all of them, but it's also picking some of the trees that as trees as well. So it's an interesting model. But if we take that and look at the ROC curve, we'll just wait for that to generate. You can see this is actually the one we've been using in the slide deck as well to demonstrate. But we can see those various points with the false positive rate and true positive rate as they go up.
And, you know, once again, we see that it moves up into the right, just like the random one did, but we've got some different characteristics. We have different trade-offs because the model has some intelligence to it. So for one thing, right off the bat, it looks like probably our first data point is getting us at around like 0.74. There you go. Yeah. So our true positive is like 0.74 right for that first data point. And at that point, it looks like we have no false positives. So that seems like a nice, healthy model. Well, by increasing the number of positive guesses overall, that is to say, by moving our threshold. So by moving our threshold, we're increasing the total number of positive guesses, and that results in some false positives. But for a while, it still seems to be a really nice trade-off. And that the slope going more up than sideways is kind of a visual indicator that we're getting a nice trade-off. But eventually it really gets flat. And for every single kind of move of elevation, we're taking huge strides in the horizontal, which means we're getting we're adding a lot of false positives in exchange for getting more true positives. And obviously that starts to be a very bad trade-off.
Yeah, in that case, it would mean we'd be sending out more rescue teams to pick up the hikers that don't exist.
Right.
Yeah.
Exactly.
Cool. So that's how I look at our ROC curves for those particular scenarios. We'll come back to ROC when we look at AUC in the next section.
All right.
Let's switch back.
That brings us back to the slide deck here. And comparing and optimizing our ROC curves. And we mentioned this a little bit before, but when we're looking at tuning our model, we start to think again about moving those thresholds. So we can move those thresholds and we can improve the model, but at some point we want to compare them to each other. So we've got multiple models, maybe similar models, but we have different hyperparameters. So a different number of trees in our random forest, a different amount of depth to those trees, a different learning rate in our logistic regression, right? So, or maybe we're comparing a logistic regression to a random forest. So we want to be able to take these different models and compare them apples to apples and say which one is better. And of course, better is a little bit of a hand wavy term. So how do we determine better, say, irrespective of our threshold choice? What is doing a better job overall? What model is doing a better job overall of trade-off true positives for false positives? And then we can take the overall better model and start to refine where we want the threshold. But how do we compare model to model? The answer comes with our area under the curve. So our area under the curve is the total shaded area, essentially. So let me grab that laser pointer again and try to grab that laser pointer again. There we are. And notice how that perfect model of ours, the area under the curve is the entire graph. And the random model, the area under the curve, is half of the graph. So we can see that with randomness, we get to about 0.5. So our area under the curve is 0.5 of the entire graph, or half of the entire graph. Now, we could have even worse ones. We had 0 when we had the worst possible model. But generally, about 0.5 is about as bad as you're going to get. So here's our area under the curve, right, for random. Now, realistically, most of our models have more like that humpback, and they look a little bit going like this. And then we're just looking to see how they relate to each other. So when we overlay one over the other, we can start to see which one has the larger area under the curve. Or we can just, of course, look at the number, calculate the area, and look at what the number that is output is.
So going back to that previous person's question, so the possible values for AUC ROC is from 0.5 to 1. Well, it's actually close. I think it's actually from 0 to 1. 0 where you've got everything wrong in your model, and 1 where you've got everything perfect.
Yeah.
So, yeah, and being close to 1 is too good to be true. Well, I think that's the question about evaluation.
Yeah, it goes back to the previous question about, hey, if it sounds like it's perfect, is that too good to be true? Is it suspicious? And the answer is, well, depends how simple your data is. If your data is simple enough to allow a perfect model, then yay for you. You might even be able to get away without using a model. You may be able to just create a simple heuristic in code. That would be my intuition, is to say if you can build a perfect model, you could probably also just extract the model out of it and just use a code-based heuristic. But maybe there are edge cases where that's not true. We are back to another demo already. That was a quick turnaround, wasn't it?
It was. This is one of the shorter modules that we have in the series, though. It's probably the shortest of them all. But we're going to go into our next exercise, which is going to look at comparing two models. So in the past, we're just doing logistical regression. This time we'll do logistical regression as well as using a random forest, and we'll be able to compare the models using ROC and AUC. So it's going to be quite nice. Let's go through the model. So again, we're using that hiker or tree CSV data set. We'll essentially read it in. We'll split up the training and the validation data sets, and we'll do a quick run of this. So this is going to use motion on both of these models. So we'll just quickly run through this. Hopefully we've got the chart here.
Quickly, like last time.
Yeah, well, it was about a minute. We had 3 charts last time. We've only got the 1 this time. So hopefully it's going to be a little bit quicker there, Jason.
I don't know. The charts don't usually take that long to render, and I have no idea what actually did take long last time. It's never actually taken that long for us before running through these exercises either. So that's interesting.
Well, my hope is there's lots of people actually going through the exercises as we're doing them as well.
There we go.
Which is always nice. I know when we run through this individually, there's probably less people on the service.
Could be.
There we are. So there's our motion chart. So we can see we've got that overlap of if they're a hiker or not, somewhere essentially around the 1 meter per second or less. There's a little bit of overlap. So this time we're going to create a couple of models, a logistic regression model and a random forest. We'll start with the logistical regression. So essentially we're going to train the model using the logistic regression. We're looking for is hiker. We're looking for the motion data to come through with it. And then we'll call fit, which essentially trains the model. And we'll go through that training process and get the level of accuracy on the training data set as well as the test data set. And then we'll do the prediction. And it's going to take a little bit of time here. I think it's got a chart being created again. And we can see that logistic regression. This is what we're showing before in the previous exercise as well. But we can see we have some overlap between the hikers and non-hikers.
Yeah, just this is after.
Yeah. Cool. Now let's do the same thing, but this time we're going to do it with the random forest. So essentially we'll create the model using the random forest classifier. I think they're using 50 trees in this case, which is the default number of trees. Interestingly, we're using trees in both contexts, trees for the random forest and also trees because we're looking for trees and hikers.
That's right.
But, yeah. So let's go ahead and train this. I'll just execute. It might take a little bit of time. But essentially, we're doing creating the forest. We're training it. We're looking for the is hiker status against the motion feature. And then we're essentially doing the training. We're doing the testing against the data set and then outputting the accuracy.
And we can use our random forest to find our random hikers in the forest.
Yeah, but I'll just scroll back up a little bit. So we can look at the training accuracy of the logistical regression, which is 0.916, and the test accuracy of 0.888. Oops. Classic. All right. So we've got our random forest performance. The training accuracy is 1, which you can almost kind of expect for a random forest because it does do a lot of overfitting that would be very high. But the test accuracy is 0.852. So the test accuracy is a little bit less with the random forest.
And we, of course, have talked about this in previous episodes, how the random forest has such a proclivity to overfit the training data because it's very capable of fitting a complex function, which it obviously has done.
Yes. All right. So we'll go ahead and create these ROC plots of basically the 2 different models. So here we're going. I think this is the logistical regression model. And we can see it's very similar to what we had. It actually should be close to identical.
I hope so.
Yeah. And then if we scroll through a little bit more, we do the same thing, this time with the random forest. We'll see a slightly different model. I remember looking at this chart yesterday and going, this looks like it goes straight up and then weirdly around. But I think what's happening here is that 0 point in the chart is being used, and actually this here is the first data point that it has.
Yeah, I think that's the first one that we're actually getting from our experimental data points. Yeah.
Yeah. So we can see it's slightly different, and it looks slightly less under the curve as well. We'll look at that in a bit more detail. But this is where we get to ROC, the area under the curve. So we want to calculate our ROC score, basically with the different regression or the different models, one with the logistical regression, the other one with the random forest, and see those values. So we should see the scores.
And remember, it's literally just measuring the shaded area in the graph that is underneath that curve, right?
Yeah,
so how much total goodness were we able to derive out of that graph.
Right. So we've just got a value between 0 and 1. So in our case of logistical regression, 0.09369 and random forest is 0.9306. So our logistical regression is actually performing better in this particular case. And if we actually look at the charts themselves, I'll go to the logistical regression. You can see that it's actually covering more of that space underneath as well. If we look at that, the random forest, there's actually a little bit of a jump here. So there's gaps, and it would be a less area in general. But obviously we've calculated that out, and we can see the different values. Now the last thing we're doing here is the decision threshold tuning. So this is where we're actually trying to find that sweet spot for what the threshold value might be. And I want to go back to the use case that we have for today's scenario, which is that we want to find a value that represents making sure that we detect hikers when they're out there, but also minimize the amount that we don't detect hikers when they're, well, that we do detect hikers when they're not there. So yeah, we don't want to send people out looking. We want
to minimize that random work that our emergency staff would have to be doing, right? If we even think about it in terms of real life here, why would we want to minimize that? Well, if they're out on a mountain rescuing someone who's not there, then the next emergency comes in and they can't handle it. Or we send them out on 13 calls today and they are absolutely exhausted and unable to deal with tomorrow's genuine emergency. So while we definitely want to be overly cautious and make sure we capture every hiker we can, we also can't just be randomizing and exhausting our rescue crew.
Well, you actually put them in risk of their own lives in those situations.
Exactly.
That's probably the worst case for it. But here, if we look at the situation, we'll look at our true positive rate at the threshold of 0.5. Then we can see that we get 0.86. And for our false positive rate, we get 0.15. So if we change that threshold value to something else, will we get a better value for true positive rate and false positive rate? And that's what we're really looking at in this situation. So we're going to define essentially an evaluation mechanism to say, here's what we can look at for the score of a particular model. So in our case here,
I would say this is highly specific though. This is a business decision, a domain expert decision. This is not just building a model. This is not just doing machine learning here. We're to understand what the proper trade-off here is, how to even build and do the analysis to recognize what the proper trade-offs are here is very much non-trivial, is very much specific to the use case. What is the right trade-off of true positive, of finding everyone who's genuinely up on that mountain versus the randomizing your emergency crew? What's the right trade-off? How do we evaluate that? There's no.
It'll be very specific for amount. I imagine, like my national park locally here is not that dangerous. It would be very different to Mount Everest, for example.
It's in Australia. How could it not be that dangerous?
Well, yeah.
Not everything is dangerous.
In Australia, no. We're sure we have dangers. That we could have a whole conversation about that. But let's have a look at the value. So this is our score that we're looking for, and we're actually trying to find the best score within our range of values here. And in this particular case, we're going to find the index of the best score, we'll get the best threshold, and then output those details. And if we look at that, if we use a threshold of 0.7373 and so on, we'll get a true positive rate of 0.833, but we'll also get a significantly smaller false positive rate of 0.03. So if I scroll back up and look at that data for 0.5, 0.86 and 0.15 are the two values. Our true positive rate is 0.86, which is, it's better than the other rate by a little, but our false positive rate drops significantly by about to about 1/5 of what the value was there before. And that's a better outcome, absolutely. So these kinds of calculations are useful for optimizing what that threshold should be for your model. Anything you want to add to there, Jason?
Well said. We found for our set of criteria, what is the optimal trade-off? What is the optimal threshold? And it wasn't 0.5 or even particularly close to 0.5.
No, it's almost at the 3/4 mark, which I wouldn't expect.
Yeah, and super interesting that even by moving that much, we barely moved our true positive rate, which means that between 0.5 and 0.73, we were well into that flat part, that very, very well, flat and horizontal part of the curve. So we weren't eking much more value out every time we were increasing that threshold from 0.5 to 0.6 to 0.7. We weren't getting much more true positives, but we were really piling on a lot of false positives by adding those more positive guesses. Most of them were wrong.
Yeah, that's good. So we've done a fair few things in this particular demo. We've looked at how we can compare models and also how we can tweak the thresholds as well to get the optimal values for our model. Let's head back to the slides, Jason.
Wonderful. And it looks like it's time for a knowledge check. So we're going to go ahead and put the subject to the test here. We don't have our interactive testing mechanism available today, so it's just you and me.
But we'll have the honor system. Answer the question in your own mind, and see how you go. All right. So question 1: what do TPR and FPR mean? Is it A, TPR is the number of correct responses, FPR is the number of incorrect responses? Is it B, TPR is the proportion of answers that were provided correctly as true, FPR is the proportion of answers that were provided incorrectly as true? Or is it C, that TPR is the proportion of answers that were provided correctly as true, FPR is the proportion of answers that were provided incorrectly as false?
Whew, that is just a mouthful. It's hard to say. A lot of letters.
Yeah.
All right. Is our TPR, true positive rate, the number of correct responses, and FPR is the number of incorrect responses? Well, not exactly. Not exactly. In fact, no. How about our true positive rate is the proportion of answers that were provided correctly as true, and our false positive rate is the number of answers that were provided incorrectly as true. So in other words, positive means we guessed true, but false positive means that we incorrectly guessed true. And yes, that's actually absolutely correct. So it is B. What about true positive rate as a proportion? We don't have an all you can eat answer. All of the above are true. So I guess that means C probably is wrong. But let's go ahead and say, is it the proportion of answers that were provided correctly as true? And FPR is the proportion of answers that were provided incorrectly as false. Again, not quite. So B remains our best answer.
Awesome. Cool, you got that right, Jason. That's what I would expect from you. That's good. All right, question 2. What are on the X and Y axes in a ROC plot? Is it A, the X-axis has the false positive rate and Y-axis has the true positive rate? Is it B, the X-axis has the number of false positives and the Y-axis has the number of true positives? Is it C, the X-axis has the number of true positives and the Y-axis has the number of false positives?
Ooh, this one's making me sweat. There's once again so many letters: X and F and T and P and Y. All right, let's see. Is it the X-axis? Let's go up from the bottom. Is it the number of true positives on the X-axis and the number of false positives on the Y? And actually looking at B, or is it just the flip? We have two options there. One going this way and the other one just kind of flipped. So which of those looks most correct? Well, I suppose most correct of those two would be B, but it's still wrong because we actually don't have the total. We don't have the count of false positives and true positives. What we have are the rate or the percentage of the true positives and false positives versus all of the trues and all of the falses. So that is going to be A then. It's our rate, or in other words, a percentage. It is not a raw number, so it's neither B or C.
Awesome. Cool. And lucky last question for today's module and also for the series is what does area under the curve for a ROC plot tell us? A, how well the model works at its optimum decision threshold. B, which is the optimum decision threshold. Or C, it gives a summary of how well a model works across a variety of thresholds.
All right. So does it tell us about how it works at the optimum decision threshold? Well, it yes, among other things, but that makes it not the best. That makes it not the best response, I'd say. Does it tell us which is the optimum decision threshold? Again, not exactly. How about C? It gives us a summary of how well a model works across a variety of thresholds. So I say yes because it tells us how it works across a variety of thresholds, and that's why technically A, the optimum threshold, would I suppose be included in that set. But C is obviously the best answer, given that it works not just at the optimum threshold, but it's giving us information about all possible thresholds.
Well, the model working at the optimum decision threshold would just be 1 point. We're asking about the area anyway, so C would be the right answer.
Yeah, and more to the point, it doesn't actually directly tell us what is the optimum decision threshold, even though technically the optimum decision threshold, which we don't necessarily know, is somewhere in that curve, but we don't know what it is, so it's not telling us what it is. We have to define that criteria. We have to decide about our trade-offs, what we prefer in that regard. So that's obviously key. Man, and that brings us to the summary of our 9th and final module here. It's a little sad. We learned about ROC curves today. So receiver operating characteristic curves, how we can use those to kind of expand the ideas that we learned about in terms of confusion matrices. We can now expand that out and look at the same concepts across a variety of decision thresholds. Not to say that confusion matrices aren't still very useful. We'll go back and forth between the ROC curve and the decision matrix as we're fine tuning and deciding on thresholds. And we saw how to compare models using the ROC and the area under that ROC curve.
Cool. And if we look at our list, we've actually done amazingly well for our machine learning series. So this is only 5 of the actual 9 modules that we've went through, and we've learned a lot. We've learned everything from very simple regression to cleaning our data to testing machine learning models, looking at architectures like random forest, different classification techniques, confusion matrices in the last series, finishing off with optimizing model performance with ROC and AUC. A huge amount of stuff, really good foundations for machine learning as well that you can take with you into a range of fields. I know we've been working with Python, but I'll be using this on other languages as well that I'll be using with machine learning too. It's been a delightful series, and thank you, Jason, for hanging out with us for the whole time.
Yeah, thank you. It's been absolutely a blast. Hey, before we talk a little bit more about where they can go for learning more about machine learning beyond this series.
Oh, yes.
You mentioned other languages. And
and
other platforms. And that seems like an absolutely wonderful opportunity to segue into this.
Well, we have the modern web development with .NET 6. That's the next series that we have on Learn Live. It's a 5-part series with just some powerhouse presenters. Scott Hanselman, Jeff Fritz, James Montemagno, Matt Succo, John Galloway, and Myra. I'm not sure how to pronounce a last name. But every one of those presenters I've seen before, and I can just say they're just spectacular. And they're presenting on the .NET 6, which is just a powerhouse of a platform. .NET Conf is on now as well. So if you wanted to find more about .NET Conf, you can look at that. But for our weekly series, I'd recommend registering for that as well.
And so we've got Q&A going on right now. We'll take a few questions, but while we're doing that, I will also start sharing some interesting things for learning more, expanding your machine learning knowledge beyond what we had time to teach you over the last 13 and a half, 14 hours or so. It's been a while that we've been doing this since September, but we've covered a lot of cool stuff. All right, so Q&A time. Feel free to ask questions, and I will also start pulling up some cool other material for you all. We do have a question.
Oh yeah. And I think we're about to say the same thing, Jason. Do we have to have upper and lower limits of decision thresholds?
So I think what they're asking is there a theoretical limit to the decision threshold? Not strictly speaking. You could have, as we kind of talked through. I talked through extreme examples of having your decision threshold be 0.999999. It's certainly possible to do it. There's no strict reason you can't do that, but there's definitely some. In software engineering, we call it code smell, so we'll call it model smell, maybe data engineering smell here, data science smell. If you start feeling like that's your optimal cutoff, it might be something to evaluate, something to think about. What is driving things in that direction? So there's no strict limit to your decision threshold, but definitely something to be aware of. That the norms would be kind of where you'd expect them to be, right? If you kind of sort of picture a normal distribution, you kind of expect your decision thresholds to hew to that over the course of many models. You would expect some to be around 4 or 7 or 3, but hovering right around 5 and moving a little bit towards the edges. And anything extreme outliers would be extreme.
Yeah, I'm a big fan of that saying. There is no best practice, only good practice in context. And the context for us in our examples that we're giving today for the thresholds were the safety of the hikers on the hill, and also the safety of our rescue workers. And those were being used to define what that decision threshold was.
Yeah, and I think one of our mods made a great point too. Is to answer the question, hey, do we have upper and lower limits of our decision thresholds? I kind of answered I answered that question in terms of what I would expect an upper and lower limit for a final model, for a deployed model. However, if the question was more aimed at what are the thresholds we use for creating the ROC curve, then the answer is actually from the entire spectrum. So we do go from 0 to 1, from 0.000001 to, right? So because we want to see that extreme on the ROC curve. So when doing the ROC curve, we will actually use all the threshold range, even though we would not expect ourselves to use the extremes at the end of the day when we're actually deploying things. So yeah, great help from the moderator on that bonus response. All right, so let's look at also some of the places to go later. So what I've got here is actually the learning path that we've been going through for the last 9 episodes. And if you scroll down here a little bit, you'll see that when we do that, when we visit that aka.ms/learnml. Hey, there it is up on the screen. Thank you, producer. When we visit that aka.ms/learnml, we are brought to option 2. And that maps perfectly with the 9 modules that we've done over the course of the last few months. But going back up here, there's an option 1. And an option 3 for that matter. Option 1 is actually the superset of option 2 and option 3. Since you've done option 2 with us, that leaves you still with option 3. And option 3 is very hands-on and has a lot of just awesome use of putting into practice the things that we've talked about and building on them. So using a lot more classification models, a lot more types of classification models, for instance, and using them with much larger data sets. So you'll experience some slower train times, but also a lot more interesting nuance when you see those larger data sets. in practice and start putting things against each other. So highly recommend moving on to that option 3 as well, and then going through these modules. All right, so that's the remainder of this learning path, but we've got some other fantastic things from Microsoft as well. So our ML for Beginners course from our cloud advocacy team. Now this one is not on Microsoft Learn, although it uses kind of a similar sort of approach. It's very curriculum based, really, really nice. And again, it's going to lean heavily into the various libraries available to let you do heavy lifting quickly. And that's one of the really fun things about it, is using the libraries, often thinking a little bit less about the whys. I like to go into the whys, but some of these material, some of these, I should say, not all of them, some of these jump really quickly into helping you do heavy lifting with the available libraries. Fantastic in that regard. You can get to this one, actually, you can see it right here on the screen, but also aka.ms/ml-beginners. There we go, or ML for Beginners works as well. Yep. And moving on, I believe both of those aka.ms's work, as a matter of fact. There's also Data Science for Beginners. I don't actually have an aka.ms for this one. And you may wonder the difference. So our session here has been called, about understanding data science for machine learning. Now, the approach that our team here has taken is to our cloud advocacy team with the much longer content that they've created, is separate out these disciplines. So ML for Beginners is very much about jumping in and doing some heavy lifting of training models, including deep learning. The data science course, on the other hand, really starts to dig in a lot more into some of the stats work, some of the data cleansing work, some of the data engineering work, some of the real engineering work of getting machine learning models operational and into production. And not just machine learning models. There's, of course, a lot of other things we can do with data science, but it is much more about actually operationalizing things rather than just training a model. You train a model and it's nice and it works on my machine, you know, but how do we get pipelines into place that are actually working, where I can routinely clean my data, where I can routinely, as new data, new information is coming in, routinely keep that engine working so that the process is reproducible, so that we can understand our data. A lot more about visualization. So this is fantastic in that regard. And then finally, this isn't a Microsoft resource, but it's one of my favorite resources. So Fast AI has a book, has a wonderful MOOC down here, and they also have a library, but the library is very lightweight, sits on top of PyTorch, very easy to use. So I'm actually a big fan there. And I recommend going through that book and going through really anything that Jeremy Howard and team puts out there. They're super useful. Yeah, so MOOC, by the way, stands for a massively online. Oh boy, help me! Somebody help me! What is MOOC?
Yeah, course is the C.
It's an online course, much like learning courses, right? I don't actually remember what it stands for. It's an online class. So much like, of course, taking a Learn module, they have their own. Massive open online course. Thank you, moderators. Massive online open course, but curriculum, right? It's learning material.
That's some great resources there too. I'd also encourage people to go to Microsoft Learn. There's a lot of great content on there in general about some of the machine learning tools, even series on TensorFlow, which I found really great on doing things like computer vision, audio classification,
and PyTorch as well. Yeah,
PyTorch, natural language
and
processing.
TensorFlow. We've got intro courses for both of those. Absolutely.
Yeah, there's some ML.NET content as well, which is the C# libraries that you might want to use, and also some of the tooling as well. But there's a huge amount to learn on Microsoft Learn.
Yeah. And staying off of in terms of the things outside of Microsoft, which we have a ton of content on Microsoft Learn, not just for machine learning, by the way. We have tons of content just for everything, for building your cloud architecture, for deploying web services, for deploying web apps as containers, which you could actually always do, but now you can do it better and more easily scale them. So all sorts of cool, and we have Learn modules for all of that. So fantastic stuff. The last thing too, I would say is, let me bring you all to one other amazing teacher who really has defined the field in a lot of ways. And I'm searching it off screen because I didn't actually prep this screen. I just want to make sure when you search the web that nothing crazy comes up. So now I'll bring it back on screen for y'all. And Andrew Ng. So Andrew Ng actually is originally I think a Stanford professor, but has worked across the industry, just leading everything not everything, but leading so much of what's happened in the last 10 years with machine learning, and absolutely the name in training people and teaching people the deep, complex parts of machine learning, but doing it in a way that doesn't hurt. So if you want to go deeper, if you want to really, really learn how things work way under the hood, then you want to take as many Andrew Ng courses as you can.
Awesome. Well, I think that's probably our time for today's session. Let's wrap it up. Any other closing thoughts, Jason?
I think that was a lot of closing thoughts from me, so I think we're probably good. I have really enjoyed doing this. I've really enjoyed talking to folks over chat, and of course talking to you a lot over the last 2 months, Glenn. It's been fantastic, so thank you.
It's been great too. So thank you, Jason. Thanks to our producer, Rob. Thanks to our moderators and anyone that helped in the production of this. And bye for now.